In this class, node analysis method of solving a network is discussed. In node analysis method, the circuit is solved by evaluating the unknown node voltages. Once the unknown node voltages are evaluated, current through any element and the voltage across any element can be calculated. For example, if you consider this network here, the procedure involved in the nodal analysis of the circuit is first we have to select a node as the reference node. Here in this example you can see that the nodes are 1, 1, 2 and this one, which is considered as the datum node or a reference node. And out of the 3 nodes here you can see that there are 3 nodes, 1, 2 and 3, and this node is considered to be a datum or a reference node. And all the voltages, say voltage of the node 1, voltage of node 2, all these are measured with respect to the datum or the reference node. That means potential of this point, say node 1 will be V1 with respect to this node. Similarly, the potential of this point, that is potential of the node 2, that is V2, is measured with respect to with respect to this reference node. Then third step is to apply Kirchhoff's current law to each node and formulate an equation. And these equations obtained by applying Kirchhoff's current law to all the nodes except the reference node will give you a set of equations, independent equations in terms of the unknown node voltages as the variables. And these simultaneous equations can be solved to get the values of the node voltages and the circuit can be solved. In order to apply Kirchhoff's current law to the nodes 1 and 2, we know that Kirchhoff's current law states that the algebraic sum of the currents meeting at a node is equal to 0. That means we'll be assigning some directions of current as shown in this figure. So with these directions of currents, assumed directions of current, say I1, I2 and I3 as shown in this figure. Here you can see that node 1 is at a potential of V1 with respect to the reference node. So the current, you can see that this is the generally current flows from a higher potential to a lower potential in a resistor. So if you have to find the current flowing through the resistor R1, it is given by the potential of this point minus the potential of this point. That is the potential difference between these 2 points divided by the resistance. And current flows from a higher potential to a lower potential. So if this is the direction of the current through the resistance R1 is given by V1 minus 0 divided by R1 potential. So if you apply this general rule to the nodes in this circuit, you can see that I1 as marked in this figure is given by V1 minus 0 divided by R1. Similarly, I2 as shown in this figure. Here you can see that I2 is flowing from the node 1 to node 2. So this I2 is given by potential of the node 1 minus potential of the node 2 divided by the resistance connected between the 2 nodes. So it is given by V1 minus V2 divided by R2. And please note that this V1 and V2 are with reference to the, or V1 and V2 are measured with respect to the reference node. So I2 is given by V1 minus V2 divided by R2. Similarly, I3, here you can see that I3 is flowing from the node 2 to the reference node. So this potential, this point or node 2 is at a potential of V2 with respect to the reference node. So I3 current flowing in this direction is given by V2, which is at a higher potential, minus 0, the potential of the lower potential point divided by the resistance in between, that is V2 minus 0 divided by R3. So by applying these rules, you can apply Kirchhoff's current law to all the nodes in the circuit except the reference node, and the resulting equations can be solved in order to find the unknown node voltages. And once the unknown node voltages V1 and V2 are evaluated, you can calculate I1, I2 and I3 in the circuit, thereby solving the circuit. In a nutshell, are the steps to determine the node voltages. First is to select a node as the reference node. For example, here the node selected is this one, which is considered as the reference node. And assign voltages V1, V2 up to Vn-1 to the remaining n-1 nodes in the network. And second step is the voltages are referenced with respect to the reference node. So based on that only actually we are calculating the current from point 1 to point 2 as V1 minus V2 divided by the resistor in between the points. And the third step is to apply Kirchhoff's current law to each of the n-1 non-reference nodes. Use Ohm's laws to express the branch currents in terms of the node voltages. And fourth step is to solve the resulting simultaneous equations to obtain the unknown node voltages. Now let us see a numerical example in order to understand the nodal analysis of solving a network thoroughly. So the question is to calculate the node voltages in the circuit shown here. This is the original network. So here you can see that we have three nodes as marked here. This is node 1, node 2 and node 3. And we are assigning this node, node 3 as the reference node, which is marked like this. So this is the reference node and we have two other nodes, and by this method we have to evaluate the potential of the node 1 and node 2, and the voltage of the nodes are assigned as V1 and V2. So the resulting equations will be in terms of the variables, unknown variables V1 and V2. So this network will be converted to, or this network will be like this after assigning the node voltages. So potential of this node with respect to the reference node is V1, potential of this node or node 2 with respect to the reference node is V2. Now, or we have to apply Kirchhoff's current law to all the nodes except the reference nodes, and the resulting equations are to be solved, or resulting simultaneous equations are to be solved to find V1 and V2. Before applying Kirchhoff's current law to the node 1 and 2, let us see how we can calculate the current as marked in the circuit. Here you can see that we are assuming that current I2 is flowing in this direction, current I1 is flowing in this direction, and here you can see that you have a constant current source. So its magnitude will always be constant. So here you can see that if we are assuming that, or we assign the unknown node voltage of node 1 as V1 and the node voltage of node 2 as V2, the currents as marked in this figure can be calculated using this formula. So I1, here you can see that I1 is flowing from node 1 to the reference node. So I1 will be given by potential of this point minus potential of this point divided by the resistance in between. It is actually given by the potential of the higher potential point minus potential of the lower potential point by the resistance connected in between. So I1 is given by V1 minus 0 divided by the resistance 2 ohm. So it is given by V1 by 2. Similarly, here you can see that I2 is flowing from node 1 to node 2. So I2 is given by potential of this point, that is V1 minus potential of this point V2 divided by the resistance in between. We have taken it as V1 minus V2 because current is flowing from a higher potential to a lower potential. So it is with respect to this direction of current, assumed direction of current. So I2 in this direction is given by V1 minus V2 divided by the resistance in between. Here it is 4 ohm. So by applying the same principle, you can calculate the current flowing from node 2 to the reference node through this 6 ohm resistance as V2 minus 0 divided by 6. That is V2 minus 0 divided by 6. Now we have this I1, I2 and I3 as marked in this figure. Now if you apply Kirchhoff's current law to node 1, here you can see that according to Kirchhoff's current law, the algebraic sum of the current meeting at a node is equal to 0. Here we are assuming that the currents flowing or coming into the node is taken as positive and current flowing out of the node is taken as negative. So by applying Kirchhoff's current law to the node 1, you can see that 5 ampere is coming into the node and I1 and I2 are flowing out of the node. So the resulting equation will be 5 minus I1 minus I2. Here you can see that 5 ampere is coming into the node or flowing into the node and I1 and I2 are flowing out of the node. That is why we have taken it as minus I1 and minus I2. So this is the first equation. 5 minus I1 minus I2 is equal to 0, which can be rearranged as 5 is equal to I1 plus I2. Or if you substitute I1 and I2 in terms of the unknown values or unknown node voltages, I1 is given by V1 by 2 and I2 is given by this formula. If you substitute that here, the resulting equation will be 5 is equal to 3V1 by 4 minus V2 by 4. You can mark it as equation A. Now if you apply Kirchhoff's current law to the node 2, you can see that a current of 5 ampere, a constant current source, or this 5 ampere current is flowing out of the node, and this 10 ampere current is current from the constant current source is coming in, flowing into the node, and I3 is flowing out of the node and I2 is coming into the node. So according to Kirchhoff's current law, the resulting equation will be this one. Here you can see that 10 is coming into the node, so we have plus 10 here. I2 is also coming in or flowing into the node, so you have plus I2 there, and I3 is flowing away from the node, so you have minus I3, and this 5 ampere current is flowing out of the node, so you have minus 5. That is equal to 0 according to Kirchhoff's current law. And if you rearrange that, you get it as 10 minus 5 is equal to 5, and I2 minus I3 there, and if you take on to the other side of the equality sign, you get I3 minus I2. Now you can substitute I3 and I2 in terms of V1 and V2 from these equations. So we get this equation. Phi is equal to, here you have I3. I3 is V2 by 6 minus I2, V1 minus V2 by 4, and you get this equation. Phi is equal to minus V1 by 4 plus 5 into V2 by 12. You can mark the equation as B. Now you have two equations A and B in terms of V1 and V2, and these are two simultaneous equations in two variables, and you can solve it either by substitution method or by Cramer's rule. If you solve it using substitution method, this is the solution. So first we will be multiplying this with equation B is multiplied by 3, and we get this equation. And this is equation A. If you add these two equations, you get 20 is equal to 12 V2 by 12. That is, V2 is equal to 20 volts. Now this value is substituted in equation A, which gives you V1 is equal to 40 by 3, which is equal to 13.3 volts. Now you can see that we have evaluated the node voltages V2 as 20 volt and node voltage V1 as 13.3 volt. Now let us see how this can be solved using Cramer's rule. Cramer's rule for three equations in three unknowns is given by this solution of the system. These are three simultaneous set of equations in variables x, y and z. You might have studied this in mathematics. And the solution for this set of simultaneous equations is given by x is equal to dx by d, y is equal to dy by d, and z is equal to dz by d. Or you can call it as, say, delta 1 by delta. Say, x1 is equal to delta 1 by delta. Similarly, y is equal to delta 2 by delta, and z is equal to delta 3 by delta, where delta is this determinant of the coefficient matrix. Here you can see that the determinant of the coefficient matrix will be given by A1, B1, C1, this determinant. And the delta 1 is obtained by replacing the first column with this column matrix. This column matrix D1 and D2 is substituted here in order to evaluate delta 1, dx or delta 1. Similar is the case with dy or delta 2. Delta 2, here you can see that the second column is replaced by this column matrix. Second column is replaced by this and you get delta 2. Similarly, this column matrix, the third column is replaced by the column matrix. So this is delta 3. And the solution is given by x is equal to delta 1 by delta. So first this determinant delta is evaluated, then delta 1, delta 2 and delta 3 is evaluated by replacing the first, second and third columns with this column matrix. These are the equations we obtained from the previous step. This is equation A and this is equation B. And if it is rearranged in matrix form, you get this matrix equation. So, and according to Cramer's rule, first you have to evaluate this delta. Delta is the determinant of this matrix and it is evaluated like this. You can see that it is delta is equal to 1 by 4. Now, delta 1 is obtained by replacing the first column with this column matrix. So, this 5 and 5 is replaced like this. Instead of this column, you have this column. Now, this determinant delta 1 is evaluated as 40 by 12 and delta 2 is obtained by replacing the second column with this column matrix. So, this is delta 2 and it is evaluated as 5. Now, the voltage unknown variables V1 is obtained by delta 1 by delta, that is equal to 40 by 12 divided by 1 by 4, it is equal to 13.3 volts. Similarly, V2 is equal to delta 2 by delta, which is equal to 20 volt. We are getting the same result. And using Cramer's rule, it will be easier to solve equations, especially in cases when there are more than two variables. For example, if we have a network with 3 loops or 3 node voltages, in that case you will be getting a set of 3 equations in 3 unknowns, and it will be difficult to solve the equations by substitution method. There it will be easier to use Cramer's rule.